Good morning, everybody. This is Mr. Steele, and I'm not here today. So instead, I've decided to record the lesson for you so that you'll still be able to keep up with everything and so that we won't have to play catch-up tomorrow. As you already know, the test for this unit for Chapter 8 is going to be held a week from tomorrow. So I figure it's better to make sure we stay on track with everything, and that way tomorrow we can review a little bit, fill any small holes that we have, and completely stay on track. So anyway, this will be Note 66. I asked that you please record it just as you normally would in your notebook. Unfortunately, you won't be able to ask questions because if you do, well, the DVD player is not going to be able to answer you. So yeah, that would be awkward. So instead, what I'd recommend is, again, just take notes, and then tomorrow I will be back and be able to answer your questions for you. So again, this is Note 66. This will be the last lesson that we have on solving log equations, and this time we will be solving pseudo-log equations. Which, as you'll see in a second, is really just code for having logs on both sides of the equal sign. So logs on multiple logs, multiple sides. So in order to start this off, obviously, right now I'm trying to buy you time so that you can copy down anything that you need here, including the essential question and the title and everything. What will really help us kind of get started off here is to go back to the very first day that we started this unit. Well, technically it was like the second day. But at the same time, what we did is we faced equations that look like this. If you remember, they actually had a little equal sign in there. At the time, and that was just kind of weird. But the idea was we were supposed to try to solve this equation, figure out what the power was that goes up there. Now at this point in this unit, you can obviously very quickly jump and say 3, x equals 3. And yes, you're absolutely right, x does equal 3. Good job, pat yourself on the back. Not too hard because that would be a slap on the back. It wasn't that special. So, what is it that we're supposed to do? Well, in reality, when we did this problem, we were supposed to look at this, 5 to the x equals 125, and see that this equation is the same as another equation that's very similar to it. In fact, all we did was change the form of 125. 125 is 5 to the third power, and by getting to 5 to the third power, we're able to do this thing. We didn't talk about it all that much, and we're still not going to, really. But the idea is we'd go, oh, 5 to the power x equals 5 to the power 3. They have the same base. Like, they are both base 5. So, in fact, what that left us able to do was just kind of cancel them. We just went, well, they're not important anymore. Same base, same base. Like I'm doing those little quote things with my fingers, but you can't see it because this is just a camera on this thing. We went same base, and then we were able to take the exponents and set them equal to each other. And we'd get that x equals 3 in this case. This would be pretty much the easiest possible question that we could ask you from one of those things. So the idea today is that we're not going to do it in the same context because, you know, we already checked the box with these guys in it. Instead, what we're going to do is we're going to see what happens when we have log equations where the same sort of relationship is happening, where we have the quote-unquote, again, the fingers are doing that thing, same base for both sides of the equation. So in other words, we're looking at the same type situation as an equation like this. Go with log base 2 of x equals log base 2 of 11. Basically, the idea is when we look at this equation, and again, we're not there yet. We've still got plans to go through. We've got some definitions. We've got all sorts of stuff, some examples and everything. But the idea is when you look at this equation, the thing that you should recognize is that the bases here are the same, just like they were in the previous example with the common bases. The difference is now we don't have things in exponential form. We have them in logarithmic form. So the question will be, well, what kind of catches are there? How does it get difficult? Like, are there problems? What issues will there be? So our goal for today is to not only just solve simple equations like this, where we can just kind of think our way through and figure out that x equals 11, but to actually figure out a strategy for going through any problem that has logs on both sides of the equation, and then, of course, to be able to practice that skill as well, and complete kind of our understanding of all the different solving techniques we'll have for log equations. So again, our goal for today is to master the pseudo-log equation, which looks a little bit like this. Okay, so with that little bit of introduction out of the way, let's first get to a definition, because again, I'm using this thing in the title. It says pseudo-logs, and the question is, well, what is a pseudo-log? Well, to start out with, you might want to think about the prefix, and I think it technically is a prefix, the word pseudo, because pseudo is an important word here. Basically, pseudo means fake. You might have heard the word before, used in the context of like pseudo-psychology, something like, I don't know, fortune-telling, palm reading, those kinds of things are pseudo-psychology because they pretend to have some sort of insight into the world or into the mind, when in reality they're just, well, I don't want to insult anyone that's a fortune-teller. If you're a fortune-teller in here, raise your hand. Ha, I can't see it, so it's kind of a joke. But basically the idea is it's something that's fake. In other words, if something's a pseudo-something, it's not really what it may appear to be. Therefore, when we talk about pseudo-log equations, we're basically saying that they are fake log equations. So it's a little weird to get used to. But as far as recognizing them, they usually stand out pretty well from the rest of the pack of equations that we have out there. A pseudo-log equation will have logs on both sides. But they can't just have the same, or they can't just have logs on both sides. That's not enough. And the reason for that is if they don't have the same base, then we really have some sort of weird relationship going on. We may or may not even have the tools in Algebra 2, or even as far as like pre-cal, to actually figure that out. So in other words, they have to be logs on both sides with the same base. And that should make sense to you, because if we think back to solving same base equations, obviously if this had been written as 5 to the x equals 38, we would have had to use different techniques, some techniques that were a lot more advanced than just looking at it and decomposing a number like 125. In fact, we'd have to use logs, but where do we go from there? So again, what we're going to be looking for here, we're going to be looking for the equations that have logs on both sides, and to make sure that those logs have the same base. It could be base e, it could be base 7, it could be base 42, it could be base 3.14159. It doesn't matter. It could be any base, as long as, of course, that base is a positive number, because as we learned a couple days ago, you can't have a negative base in logarithms. It's just part of the complete definition that we have. So pseudo-log equation will have log on both sides. This guy, log base 2 of x equals log base 2 of 11, is a very simple pseudo-log equation. And why do we call it a pseudo-log equation? Well, because basically those logs don't matter. As long as they're the same base and they match, we can actually do the same things that we did before. And we can say to ourselves, if I've got the same base on both sides of the equal sign, x equals 11. So we're actually able to use that same kind of thing that we did up here when we had the common base problems from before. So now the restrictions don't go, this is easy, I can just start slashing logs. No. That might qualify you for a lumberjack license, but it's not going to actually solve the problems here. There are some more little catches that we need, although the skill itself does amount to slashing out a bunch of logs. So let's take a look at all the complete set, or the complete situations that we might run into. Well then, so now that we've gotten some background information here, let's drop down and take a look at some examples. And I'm basically going to hit an example of pretty much everything and then try to build in a little bit of time for you to try a couple yourself and then go through them as well. Before we start though, it's something we just have to kind of pay attention to. As I mentioned it a little bit before, that although we seem to have this really cool idea that, hey, if there's logs on both sides, we just slash them out and we just cancel stuff and it's all good. Yeah, we do. The problem is that situation's not going to come up every single time right away. We may have to do a little bit of work in order to get to that point. So this little warning I'm going to leave on here on every slide if I can is just to remind us that what we have to have in order to use this slashing attack is we need to have a single setup every single time. We need to every single time have log base b of something equals log base b of something. So normally I'd write like stuff and stuff in there, but in reality what I'm saying is that we can't just do it right away unless we actually have this perfect little situation set up. Unless we have the log equal to log, they have the exact same base. Like you can probably see it right there. They've got to have the exact same base, because that allows us to do that little same base trick. And wow, that's an ugly arrow, isn't it? Jeez. Got it. And then, of course, it doesn't matter what's in the arguments. We just have to go through and do it. At the end, we'll start to worry about all that other stuff. Like, did that argument work? Was it negative? Were there any issues that we saw as we went through? So, just remember that every single time we have to have this exact setup. Otherwise, our technique, that idea that we'll be able to slash the logs because of the same base, will not apply. We have to make them look like that first. So now what's going to happen is I'm going to write out an example here, and then we're going to look to solve it. But the problem that's going to come up is that I'm going to write out a plan, and that plan is going to involve a whole bunch of pieces. It's just that in this problem, it may not involve all those pieces. So just trust me when I say let's write down the plan, get it all in there, and then we'll look as we go forward at all the different places where we might need to use those steps. So to start off with, let's write our first example for the day. Instructions will always say solve, and they'll usually remind you to check for extraneous solutions, because that's always a possibility something might not work. We might have a negative argument in these problems. But at the same time, we're going to solve. And we're going to solve, let's see, how about this guy? Log base 5, 3x plus 1 equals log base 5 of 19. Okay, so here we go. So as we look at this guy, again, our first place we're going to start is we're going to start by kind of writing out a plan to work with all these guys, to work with on this problem. And again, you kind of have to trust me that some of these steps we're not going to be able to actually look at just yet when we start this problem. Because again, you might already see it. This is a pretty easy problem. They already have the same base. So play along. So, well, let's see. The first step we would normally need to do in any log problem, not this one though, is to make sure that we power law in any coefficients. Yeah, it's not going to be enough room to write the word coefficient. So what I mean by that, or what I mean by this, it's a little awkward when you're talking from a different day, is basically we've got to look in front. We've got to see, is there any number out in front here that might be keeping us from having an empty space in front of each log? So in other words, if there was a 2 out there, if there's a 3 out there, we would have to bring that power in. Well, in this case, we don't have anything sitting out there. So it's like this first step is already taken care of. We don't have to power law anything. The second step, again, something that we may not have to do in this situation. Our second step, that's a terrible circle. Our second step is going to be condense so that our equation just looks like log base b of stuff equals log base b of stuff. So again, why do we expect that? Well, it says it right up here that we've got to make that happen. So basically the key elements in this line, in this step of the plan or the strategy, is going to be to make sure that we have the same base, which as it shows right here we do. We have the same base. And of course we're already condensed. Like there's only one log on each side, so in fact we're already there. Step 2 is also taken care of, which is kind of nice. Again, these are steps that we'll need as we go forward. For now, we're okay. Once those first 2 steps are out of the way, those are ones that make sure that it looks like our special warning problem up here, then we can finally do the trick. We can use that step from common bases. So we go same base, and we lumberjack all those logs. Same base, same base. So what I mean is we look at it and we go, oh, they have the same base. It's base 5, log base 5, log base 5. That's the same thing as base 5, base 5. What does that leave us with? A new equation. 3x plus 1 equals 19. So see, in reality, that's why we have the pseudo log equation. Like, that's why it's called a pseudo log. It's a fake log. In other words, those log base 5 there, they were just distractors. You know, it didn't really matter that they were there. Well, it did matter, don't get me wrong. It did matter that they were there. But it didn't, those base 5s, it could have been base 7. It could have been base 99. It could have been base 0.3. It turned out that the logs there just were part of the relationship. They weren't part of the actual solving of our equation. So from there, once we get down to that step, we can go forward and do the piece that we're very used to. We can actually do the solving. So in this case, we just use any algebra that we know in order to solve for the equation. In this case, the algebra is as simple as 2-step equations. So I'm going to subtract 1. And I'll do it in depth because I'm not here in case anyone wonders. We'll have 3x equals 18. Again, what did I do? I made a 0. And then last but not least, we'll divide by 3 or multiply by 1/3, your call. We get x equals 6. And it appears that, hey, we've already solved our equation. So, x equals 6. It seems like we're done, right? Well, in fact, we are done as long as everything meets the complete definition of the log, like that we haven't violated any of those requirements about the base or the argument. So our last step is to make sure that our argument is positive. So what I mean is we actually just look back and say, well, if x equals 6, what happens inside the logs? And that's all I'm going to worry about here, because realize, since we have pseudo logs, as long as they're logs in the beginning, they have a positive base, so it's only the argument that we need to worry about. So take a look at this guy. If x equals 6, it's like I'm going, okay, here's my potential solution. If x equals 6, I go up and we say, okay, well, what would this argument be? Well, 3 times 6, and again, this is probably in my head. I'm not probably writing it out for the most part. 3 times 6 is 18, plus 1 is 19. So 19 is positive. So in other words, I can check it off. That looks like ist. So 19 is positive, so we can check it off. that base argument works. On this side, 19 is definitely positive, so it works as well. Therefore, both arguments are positive, so we haven't violated any of the definition of log, any element from the definition of log. So we have our answer. In this equation, log base 5 of 3x plus 1 equals log base 5 of 19. We have that the answer is x equals 6. And so we have, in fact, solved the equation, which is nice. Like, we've got an answer to the equation. So with that said, yes, when you look at this, all these pretty colors, you're probably just thinking mostly about that slashing, like, yeah, yes, slash the logs. Okay, don't overdo it. And that's speaking to you, not me. Obviously, I didn't overdo it with that egomaniacal laugh. Excuse me. But basically the idea is don't just jump into that. We're going to have to do some other stuff first to make sure that we meet this warning. Otherwise, as those radioactive symbols tell you, bad things can happen. So let's take a look at that next. Okay, so now before we move on, there's one thing that I did add in here that might be worth noting, and it's this little piece up here. Like, if you look at it, you might just say, well, what all you did was write the word plan. Well, yeah, I did write the plan, but I also pointed out when this works. So again, the most important thing up here, as we said, is that there's only certain times when we're able to do this slashing the logs, when they have those common bases. So we can't just do this when we see logs on one side or anything. This is only going to work when we have logs on both sides of the equations. So pay attention to that as you go forward, especially as you get to like the back side of the homework or on a test or a quiz when you're asked to solve a whole bunch of equations. This idea is only going to work when we have logs on both sides, and of course that they have to have the same base. So just keep note of that, and as we look at the second example, as well as all the other ones, I'll keep that up there off to the side so we make sure we can always refer back to it. So our second example, what are we going to do? Well, let's get to one that involves a little more bells and whistles, maybe some more interesting stuff going on here. So we'll go to this equation. So we want to solve ln of 3 plus the ln of x plus 2 equals the ln of 45. And now if you're like a lot of people, when you see this, right off the bat you might go, oh god, that's that ln thing, the natural log, it sure doesn't sound natural to me. Yeah, all that stuff. In reality, sure, yeah, we know natural log isn't normally our friend, but in this case, because it's going to be a pseudo log, which I can tell already by noticing that there are logs on both sides, all with the same base because they're all ln. That tells me that really the e part isn't going to matter at all in this problem. All we're looking at is a pseudo-log equation with the natural log instead of some other base. So in other words, don't be intimidated by that guy. It might as well be log base 88 for all we care. So looking at this guy, according to the plan, our first thing is to power law in any coefficients. So again, I'm looking in front of the logs to see if there's anything sitting there. Well, there's nothing there, there's nothing there, and there's nothing there. So in fact, I don't get to do anything. That first step is again left unused. So fine, whatever, be that way, your call. So we don't need to do anything in the power law. We've already got it done. The second step though, right here where we condense to log base b equals log base v, we are going to need. And the reason I know that comes from the fact that I've got two logs over on the left side. And it only works, as it says everywhere here, it only works if we only have one log equals that same log on the other side. So we need to first condense this to one log. Well, we use the condensing rules, or the log laws. This would be just the sum one, because I've got a plus sign right here. This left side is going to condense, as you've done many times, to 3 times x plus 2. Our new argument will be that guy. And I'm putting in brackets just to emphasize that that whole thing is in the brackets. And of course, it'll still be equal to ln of 45, which isn't touched at all. So how does this work? Well, now we can basically go through and we can simplify this guy so that we can use that same base fact. And we're almost there. So on the left side, once I distribute a little bit, we're going to get the ln of 3x plus 6 equals the ln of 45. And now at this point, I can kind of take a deep sigh, or a deep sigh of relief. That's what I meant. Because now the equation looks just like this guy. A little bit different, ln instead of log base 5, but in reality it's the same as that last equation. So I can go ahead and go through and evaluate this guy the same way. So what that's going to look like will be the same thing. I go, what base is this? Well, natural log is base e. Natural log is base e. Oh my gosh, they've got the same base. Same base, same base. That's what we wanted. That leaves us with this equation. 3x plus 6 equals 45. They were pseudo-logs all along. They weren't even real logs. They were just pretending. I don't know, they were stumps that dressed up like logs. I don't know. I don't know where to go with that, so I'm just going to leave it and pretend that I didn't say it. You can't give me a funny look if you can't see me. Got that one figured out. So from here, what do? Well, we did the same base. We got rid of the logs. It was all just a fake log anyway. Now we solve. So minus 6, make a 0. We get that 3x equals 39. And if memory serves, 3x equals 39 when x equals 13. So once again, it would appear we have found our solution. Like we got it. We just had to condense first, and then we had a pseudo log ready and waiting for us. Now at the same time, though, again, don't forget this guy. Let's make sure that the argument is positive. So let's go back and figure it out. So looking at all the arguments, 45 is good. Like it's definitely positive. Last time I checked, 45 is a positive number. If I have $45, I'm not yet bankrupt. Same thing with 3. If I have $3, I am not broke. In here, though, we have x equals 13. So we need to see what happens when we do 13 plus 2. Well, 13 plus 2 is going to be obviously positive as well. So since it's positive, in fact, this last step is checked as well, and we have our answer. There was nothing about x equals 13 that made an argument negative. So voila, we have our answer, x equals 13. So again, we started out with something pretty complicated looking, but because there were logs on both sides, once we condensed it down, which we did right here, we were able to get it to an equation that was a pseudo log, and then cancel everything out and go run through and work through. So again, works out pretty nicely when you have these guys. Questions? Right, you can't ask me any questions. Or I could do that thing where I pretend like I'm answering a question from someone, but that'd just be weird, so I'm not going to do it. We'll just move on instead. Moving on then, let's take a look at another example. And again, I'm trying to hit a little bit of everything, so I think I've got like a couple examples left before we get to the triads. But I'm hoping this goes a little faster because well, I'm not here. Can't tell if it is or not. Okay, so next guy. We are going to solve 2 log of x equals log of 121. So there's our first equation that we want to attack. We want to attack this guy. 2 log x equals log to 121. And you're probably sitting out there writing it down, trying to listen to this at the same time, even though I realize I'm making it hard on you multitasking. And you're probably thinking, this one looks way easier than the last equation. Look how many more logs there were before. Like, how in the world is this going to be a hard equation? In reality, it's not a hard equation. But the problem is, having this 2 on the outside finally forces us to see the need for step 1. So that 2 out there, we can't just start slashing logs here because that 2 in front isn't 2 times x. It's 2 times the log of x. So if we want to go anywhere, we have to do step 1 finally. This is key, and I'll tell you what, this is one of the most missed things every single year. People screw this up all the time. Even in calculus, it's easy to screw this up. So what do we need to do first? Well, we need to use the power law. If you don't remember the power law, it basically says that if you have log, or sorry, I'll write it this way. You have n times log of x, that's equal to the log of x to the n. Basically, coefficients become, that's bad, just a second. Coefficients become powers. What was times becomes a power. And the reason for that has to do with the first log law about the summing, because if you add up a certain number of things, it works out that way. Not as relevant to us right now. The most important thing for us is that we are not going to be able to handle having that 2 out in front. So what does that mean we need to do? We need to go ahead and get rid of it. So we need to use the log law right away so that we have a log equals a log. So I'm going to take that 2 and bring it up on the inside. What does that give me? It gives me log of x squared equals the log of 121. And so now we've got that first step out of the way. So, and if you don't trust me, like, check the answer at the end with mine and then check it on yours and you'll see that my way worked. Okay, so the second step, I should probably be not showing you the colors because it gives it away. The second step we don't need at all. The reason for that is we have log base b equals log base b. In this case we don't see it, but this is really log base 10 and log base 10 because these are both common logs. So in fact we don't even need that second step. Just out of this problem, it wasn't necessary here. Now we can use the same base thing. So what are the bases? Well, as I said, they're common logs, so they're 10. So, same base. That leaves us with x squared equals 121. So that's fantastic. We're able to reduce the equation down to something pretty simple. X squared equals 121. There's like 6 different ways that you could solve this. I'm going to just go with the square root method. So we take a square root on both sides to get rid of the squared. That leaves us with x equals plus or minus the square root of 121, which is 11. And so now we go, okay, got it. Now we just need to go check and make sure that the argument is positive. So again, recapping what we did, we used the power law to bring in that 2. Then we used this pseudo log stuff to cancel the logs because they were the same base. And then we solved the equation through whatever method we had, which happened to be square rooting, and we got x equals plus or minus 11. Well, if we check positive 11, obviously 121 works, but we've got to check the argument over here. Does positive 11 leave the argument positive? Well, yeah, it does. Obviously, it leaves the argument positive because positive 11 is positive, so we can take the log of a positive number. The other answer, though, that negative 11, if we put that in there, negative 11 would leave us with log of negative 11. We cannot take the log of a negative number, because the argument would be negative. We talked about why that was on Tuesday. So in fact, this guy, the negative 11, doesn't work. Our real answer is just x equals positive 11. And so oftentimes I like to write it this way just to be able to indicate, hey, there was an answer that didn't work out and I'm aware of it. Give me points. Well, nobody gives me points anymore, but whatever. So it turns out only 11 works. And now looking at this, you may be bored out of your mind. You might be just saying, okay, how long till we get to the last example? But you may also be looking at this going, why is it that negative 11 doesn't work? Because we had log of x squared. We'll realize this was not the original equation. So not original. What was the original was this guy. In this original equation, we didn't have the 2 on the inside. It wasn't squared. Had it been, maybe things would have been differently. But for now, because we had to bring it in, that meant that our equation was changed a little bit, and in the original equation, leaving negative 11 would have left us with a negative argument. So in fact, only 11 works in this particular problem. So there we go. So finally, on to our last example. Let's move it down. Why don't we pick a ridiculously hard example here? Maybe one with 17 separate logs. That'll get you. No, let's just pick one that helps us hammer home all these concepts real fast. Let's go with the log of x squared equals 2 log of 4. So this is going to be our final big example, although I will let you work on the triads and then do the triads for you afterwards, so you'll have a couple extra to look at. Basically, here we go. Log of x squared equals 2 log 4. So looking at this guy, let's see, what's the first thing I need to do? Come on, somebody. Come on, someone, just, like seriously, look at the plan. Oh, yeah, you're right, you can't answer me because this is all pre-recorded, so how embarrassing. Oh yeah, okay, so first step, let's do the first step right here. It says to use the power law. So we have to look and see, is there anything in front? Well, there's nothing in front of that log, but there's a 2 in front of that log, so we got to go out to that one. That's the one to look at. So we're going to take this guy, we're going to bring him, or her, I guess 2 could be either one, up into the equation. So what is that going to look like? Well, it's going to look like the exact same equation. Why don't I just do this? It's kind of fun. Use the copy and paste feature on your pen or pencil. So we're going to use this guy. It's going to be the exact same equation, except we're going to have moved that number up inside. So our new equation is going to read the log of x squared equals the log of 16. Because 4 squared equals 16. If you're not sure, check your calculator. Go ahead. Yep, 4 squared 16 still. Nothing's changed there. So good deal. Okay, so next, looking at the plan, we've done step 1. We've got the power law taken care of, condensing it. I'm going to say it's done. Let's go ahead and same base it. Why not, huh? Same base this puppy. So log base this base 10, this base 10, same base. Logs are slayed. That leaves us with x squared equals 16. Good. No more logs. It was just a fake log anyway. Nothing to worry about. So let's solve it. Boy, this problem seems kind of familiar. It's an awful lot like the last one. When we square root both sides, we need a plus or minus. So x equals plus or minus 4. So it appears that we have found our answers. But of course you go, no. I recall on the last problem that you had to check your answers because one of them was extraneous. One of them made the argument negative. So I say, okay, fine. Like, yeah, it's in the plan. Like, I guess we can look at the plan. So, step 5, make sure the arguments are positive. So let's start with positive 4. If we plug in positive 4, we get positive 16. So that works. It's okay to have positive 16. If we plug in negative 4, I remember last time the negative didn't work. See, why was that? Negative didn't work last time? Oh yeah, it was because the x was all alone inside the log in the original equation. Well, look at this guy. We're looking at the original equation right here. And in this case, putting in a negative 4 still is going to give us positive 16, which means that negative 4 also works. So in other words, we actually have two solutions to this pseudo-log equation. We get positive 4 and we get negative 4. That might seem a little weird to you, but think about it. Because we have the x squared in there already, no matter what kind of number we put in there, positive or negative, as long as it's real, it's going to spit out a real number. So both positive and negative answers are a possibility here. So in other words, just because it's a pseudo-log equation doesn't mean that we can't ever have a negative answer, but that's just it. It can be a negative answer, not a negative argument. The argument itself, in this case, x squared, that guy still had to be positive. So just happened that in this case, negative 4 did not violate that requirement. So in fact, we've now solved a fourth pseudo-log equation by using this method and plan outlined here on the right side. In this case, we got 2 answers. Every other time we got 1. So we could get lots more answers. We could get 0 answers. It just depends. So with that said, let's go ahead and give you an opportunity to just try 2 problems. Just 2 problems. Here, does anyone have any arguments? Does anyone not want to do it? Nope, nobody's raising their hand, so can't tell. Good deal. Let's do 2 try-its. So let's go down here. And I'm going to give you 2 to try. And then what I'll ask is after I do that, if if you could just pause the video for maybe 3 or 4 minutes, give them a little bit of time to go over the problems and try them out yourself, then we can go ahead and let them work on homework the rest of the time, please. So first, what are those 2 equations? Of course I know the 2 equations that I'm going to use. What do you think this is? This isn't some sort of weird operation here. I know what I'm doing. I'm not making this up as I go at all. I'm actually not. Actually, the notes right here. You can hear them, but thought it'd be funnier to go that way. So what do we have? Let's go with a hardish one first. Okay, so there's one equation. That's A. And then B. Let's go with this guy. And there's B. So I would like you to solve these 2 equations. First one is log base 3 of x minus 2 log base 3 of 5 equals log base 3 of 4. So a pretty involved equation. And the second one is ln of 3x plus 1 equals the ln of 4x plus 5. So there are 2 equations. If you could please pause for just a second. That would be excellent. So please go ahead and we'll actually pause after I finish changing my colors here. That would be great. Alright, had enough time? Good deal. I think it's time to go to the highlights of these 2 try-it problems. So let's take a look. First one. Looking here, we had a little bit of everything here. In fact, we need to use every single step in the plan. That meant you had to do all the hard work. Sorry about that. So looking at this guy, first thing that I notice is, bam, right there, I see a 2 in front of the log. That means that I'm going to have to use the power law to bring it in. Bringing that 2 up, I get log base 3 of 5 squared, which is log base 3 of 25. There it is. Next step, I've still got to condense because I've got 2 logs on the left side. If I use the log laws with the minus sign, I can go ahead and make that into log base 3 of x over 25. It's all going to be equal to log base 3 of 4, and of course that's great because we get the same base, so we just slash them right out of the way. What does that leave us with? X over 25 equals 4, and we can solve that by multiplying both sides by 25. Here we go, 4 times 25, it gives us 100. Is 100 a real solution though? Only one way to find out. We go up to the original equation, we check the arguments. 4 is positive, 5 is positive, and x, if we plug in 100, well 100 is positive too, so that works as well. Hence the check mark right there, and bam, we got it, x equals 100. First equation is solved. Second equation. Letter B. So we're going to look at it. ln of 3x plus 1 equals ln of 4x plus 5. Right away you can see that we've got 2 steps that we can immediately skip. We don't have any power laws because there's nothing in front here, except for those 2 dots. I just put them there though. And of course they're the same base. And of course there's just 1 log on each side, so there's no condensing. These guys are the same base because natural log is always base e. So we slash them right out. We get 3x plus 1 equals 4x plus 5. A little bit of slick algebra from back in Algebra 1. and you end up solving to find out that x equals -4. So you go, okay, well he said in the last one, the last example on the last page, that it was okay to have negatives sometimes, so let's just check and make sure. Let's make sure the arguments are still positive. So we go to throw it up here, 3x plus 1. If we plug in -4, we get -12 plus 1. That's -11. Unfortunately, that's a fail. If you've done it over here, if you prefer this one, you get -16 plus 5 equals -11. Well, that's great that they're all the same, but neither one of them works. So unfortunately, both of them fail, which means that we have no solution at all, because our only potential one, -4, didn't work. So the answer to B was no solution. We do not have a solution. So there we go. Exciting highlights there of the solving process. So with that said, just really quickly, let's just take a look back at everything we've done, because I'm done. So what have we done? Well, since we started, we talked about a special kind of log equation called a pseudo-log equation that relied on the same principle that using the common basing, or using common bases did. If we had the same base, we cancel them out and we just play with what's left. Same thing was true with logs, but in order to find that fake log equation, we always had to have log base b of stuff equals log base b of stuff. They had to be the same base, and there had to be a log on both sides. Otherwise, slashing the logs is not a good idea. So from here, we looked at a couple examples. One where it was just pretty straightforward. One where we had to condense first, so we had to transform this ln of 3 plus ln of stuff equal into ln of one thing, so that we could actually use that pseudo log work. We had one where we had to use a power law, or use the power law to bring in a power. Of course, if we hadn't done that, we would have gotten the wrong answer. And then one where it gave us a couple answers because there were none extraneous by having the x squared on the inside, although we did have to use the power law again. Then in our examples, we saw a little bit of everything in there. We saw a little condensing, we saw a little power lawing, we saw some same base slashing, we saw some solving. We even saw a problem where even though it came up with an answer, it didn't have a solution because it turned out that it made an argument negative. So at this point, I feel confident in suggesting that you've seen everything that you need to for pseudo-log equations. So at this point, I'm going to take a step back and ask your sub if he or she could please pass out the homework, give you the rest of the time to work on that. If you have any questions, would ask a smart friend. There are lots of smart friends that you have in there, so ask some of them too. And then tomorrow, if you have any more questions, I can look at it. Big thing I'll point out on the homework assignment is the front side is all the pseudo-log stuff. On the back, it's mixed solving or some mixed sum practice, so you get an opportunity to really see how much you understand from solving, because we've now hit all the different solving techniques. We're almost done with this chapter 8. So with that said, hope this lesson's been valuable. Hope you've been able to gain some information out of it that you might not have otherwise. And until next time, this is Mr. Steele signing off. Have a nice day. See you tomorrow.